Finding the equivalent resistance is step one. Okay, what you did for homework last night is step one. Okay, not kidding. So what we're going to be doing today is finding specific measurements of an individual resistor in one of these complicated circuits. Okay, we could either be asked to find the current, the voltage, or the power of one of these individual resistors. And we're going to look at Kirchhoff's rules, verify those. Okay, so let's say each one of these resistors, these light bulbs, has 10 ohms of resistance. Okay, I want you to calculate the equivalent resistance, the total resistance, and make sure to redraw your circuits at every step. So a lot of slacking going on in the homework. Don't just get a number on your calculator or even in your head. Like, redraw it. You're gonna need it. Get a piece of paper and redraw the circuit. You have 10 ohms. Each one is 10 ohms. Find the equivalent, the total resistance. You want? This isn't. These aren't shortcuts. We're fine. Yeah, we're finding the total resistance, but I want you to redraw it. We'll mess with voltage here in a little bit. Make sure you redraw the circuit. How to do. Make sure you redraw the circuit.
Do I have to draw like the last one?
Yep. Redraw the circuit. You should have 3 circuits on your piece of paper right now. Okay. There we go. Is how I got to 15. Now, here's why I am so adamant about you redrawing the circuits. Because in the story of Hansel and Gretel, they laid down breadcrumbs. These are our breadcrumbs. and we're going to retrace our steps to get back home. Okay. If you don't have these redrawn, it's going to be a rough way to get back. Okay. So here's how we're going to use this. At every level, we're going to find all three measurements for the resistor that I care about: the voltage, the current, and the resistance. All three of those for every level for the resistor that I care about. Okay, so here I know that the voltage across the battery is 15 volts. Therefore, the voltage across this total resistor is also 15 volts. The voltage gain is equal to the sum of the voltage drops. Okay, so we got 15 volt gain, or 15 volts across that. I'm looking for my current, and I have resistance of 15 ohms. Now, I made this so it would end up being nice, so we didn't have to do much on the calculator. So I find that to be 1 amp. Okay. So now I know I've got 1 amp flowing through here. I've got 15 volts, 1 amp, and 15 ohms for that total resistor, that total resistance. Okay, that's my total resistance. I got my total voltage. Therefore, this is my total current. Okay, good with that. Now, this guy came from the combination of the 10 and the 5. Wired how? In parallel or series? In series. What measurement is the same in a series circuit? Current. Folks, that question, the answer to that question needs to be on lockdown. Okay? That is that factoid. That needs to be like in there. Okay? So this is series, so the current is the same. So whatever current I have here, that's the same current I'm going to have here and here because these came from series. This is a combination of these two in series. So whatever this is, that's the current here and through there. So I've got 1 amp flowing through this one and 1 amp flowing through that one. Okay? Because current because in series. JP. No, not in series because in series are the same. But in what case do you add the current? Parallel. Okay. Now, so I'm looking for the current through bulb 2. Here's bulb 2. Where's bulb 2 buried? In the 10 or in the 5? In the 5. So this is the resistor that I care about. So I'm going to calculate all three things for the resistor that I care about. Okay? So I've got the resistance, I've got the current. Man, the only thing I don't have is my voltage. So I find that to be equal to 5 volts. So now I know there's 5 volts across this guy. Okay? Got all three pieces of information, all three measurements. Okay? for the resistor I care about. Now, the 5 came from the 10, and the 10 wired how? Parallel. What measurement is the same in parallel? Voltage. That is the second factoid that you must have on lockdown. Okay? So, the voltage that I calculated across this is going to be the same as the voltage across this one and that one. So I've got 5 volts across this and 5 volts across that. That makes sense? Conceptually, does that make sense? Like, these both have, because they're in parallel, both have the same voltage across that. It can't, these two boil down to this one. Okay? Now, I'm at the point where I can find the current in light bulb 2. So I have the volts, I've got the resistance. All I'm missing is the current. I find that to be 0.5 amps. Good with that? And that, my friends, is the answer at 0.5 amps. Okay. Recap. Step 1, find the total resistance, the equivalent resistance. Redrawing the circuit every stage. And then retrace your steps, finding all 3 of these measurements for the resistor that you care about in each stage. As you go back to the previous stage, if it's in series, the current is the same. If it's in parallel, voltage is the same. So you bring that measurement from this step back. Okay? Folks, if you are faithful, well, first off, if you're good with finding the equivalent resistance and you're faithful to redraw the circuit and then employing this methodology, there's no reason other than a brain fart why you'd miss these problems. Okay? This is kind of like math class. I teach you a procedure, you repeat the procedure, and you get the right answer. Okay? Does that make sense? Like, it's, there you go. This should be a comfort zone. Like, you just do it. And you're like, boom, got the answer. Okay? In my opinion, the only thinking needed is bringing it down to this point here. After that, you just repeat this procedure. Okay? Here are the 3 pitfalls. If you're going to miss this, here's why. Number 1, somehow you didn't get the right answer at this point. 2, because you didn't redraw your circuits. Okay? And that might have been the reason why you got this one wrong in the first place. Okay? The third pitfall that I've seen a lot of students do is they successfully make it to here. Bless you. Okay? And then they calculate this, the total. And then they prematurely take this information from the total and jump all the way back to the beginning and not retrace their steps. Okay? those three things are why you're going to miss this problem. Okay? You must retrace your steps at every level. Okay? Good with that? Okay. Before I erase all this, I want to show you how Kirchhoff's loop rule and junction rule are applied. Okay? So Kirchhoff's junction rule or loop rule says this. Well, before we do this, I need to calculate all three things for every resistor. So here, I've got 10 ohms, 1 amp, excuse me, so I'm going to use the same procedure and find that to be, there's 10 volts across this guy. Are we all right with that? Okay, so this light bulb is actually this light bulb. So this is 10 volts across this, and I know there's 1 amp going through this one. Okay, this light bulb is identical to this light bulb. We found that this was 0.5 amps through this one. Oops. So Kirchhoff's loop rule says for a single loop, the voltage gain equals the voltage drop for a loop. Okay? So I'm going to start here. I got a voltage gain of 15 volts. This is my chutes and ladders. Okay, so I have a 15 volt gain climbing up a ladder. And then here I have a 10 volt drop. So a slide. And then I've got a 5 volt drop. Another slide. And then I'm back here. The voltage gain equals the sum of the voltage drops. Okay, that will always happen. Let's look at this loop. Here's a second loop. Voltage gain, voltage drop, voltage drop. If that doesn't work out, you did something wrong. So go double check. Okay. Kirchhoff's junction rule says this. The current in equals the current out. The only junction is really here. There's one right there too, but it's identical in terms of what's going in and out. So here we've got current ins going this way. Current in is 1 amp. Current out, both of these are going out of that junction. I've got 0.5 amps here, and I've got 0.5 amps here. That will always work as well. So if you get desperate and you're like, oh, I don't know, like those two are tried and true, those will always work. If they don't, that leads you to like where you messed up. Okay? Questions there? Ready for this to go away? Okay. If year one is like, I don't know what to do on the homework, take a picture of this. If you know you tend to get lost in the homework, you're like, whoa. that it's on canvas as well, but okay. So that's all. That's the procedure. Okay. Just did that. All right. This one's on you. Go. Beat me to the finish line. Okay. Redraw the circuits. I will give you a head start. Four-thirds ohms. How do we do? Thumbs up if you got it. Great question. You can put it as 1.33. It's totally fine as well. Call me over if you didn't get 1.33 or four-thirds. Okay. If you're good, start working backwards. I want to know the power through the 5 ohm resistor.
I got 0.75.
You need to find the inverse. Reciprocal of that. There.
Oh, whoops.
That makes sense. You found 1 over.
I said
Yeah.
Let's just look at it as a decimal form.
It was
Mhm.
not correct.
Do that.
Yep.
Wait, it's the answer's
Oh, yeah.
voltage.
That is, yeah, it's really close to 12.
Okay.
Just around at 12.
Okay. Yes.
What?
That's the answer.
No.
Wait, so
That's-
find the voltage. What's power dissipated?
Okay, so power is equal to current times voltage. Okay.
Exactly like you. Like, is there multiple ways of drawing this? Because I put it differently, but I still got the same answer. Because I did.
Yeah, that's fine.
Combine these two,
Yep.
and then I did this one. And
Yep.
then, okay.
Perfect.
So we have to work backwards now that we got 12, or can we just multiply it by the current?
Don't work backwards. That's the pitfall.
Yeah, I don't know what's here. Well, okay, if this would be like, since voltage is the same, that'd be 12, that'd be 12.
Yep.
But that'd be 6 and 6.
Yeah, this is where you retrace. This is where you're.
It's 6 and
Yep. So find everything about this. It's 12 volts. So find your missing thing. Okay, here we go. I know there's 9 amps going through here, therefore there's 9 amps going through here. Okay, I'm missing the voltage. So I've got 9 amps times 4/3 ohms. Find that to be 12 volts. Okay. So my total voltage is 12 volts across here. Now, if I take this, okay, catch this. Here we go, ready? If I take this and I jump all the way over here, so there's 12 volts across that, or I just take, hey, 9 amps and multiply it by 12 volts. That would be the total power dissipated by the entire circuit. I don't want that. I just want how much power is dissipated by this one. If I took this 12 volts and applied that across here and then found the power with that, I would also get it wrong. Okay? You must retrace every step and find the missing measurement for the resistor that you care about. Okay? So I've got 12 volts here. So that means I've got 12 volts across this one, 12 volts across this one, and 12 volts across this one because these are wired in parallel. The resistor I care about is the 5. The 5 is buried in the 6. So I need to find all 3 measurements for the 6 ohm resistor. Find that to be equal to 2 amps. Ben. I multiply what by 5, 6? Nope. Nope, they're not. It's not proportional like that. Okay. So once you have this, These two are wired in series. So I've got 2 amps going through this one and 2 amps going through this one. I care about this guy. Voltage is equal to current times resistance. I'm looking for my voltage, have my current, have my resistance. On my voltage drop across this to be 10 volts. Okay. But I'm looking for the power. So power is equal to current times voltage. Power, I know both of those. I've got 2 amps going through that guy, and then 10 volts going across that one. Power is equal to 20 watts. How did we do? Okay. That's what your homework's going to feel like. Okay. Several steps, but they're not complicated. If you lay out your problem and repeat those steps, you should be fine. Okay.